Hello class, today we're going to be talking about points of concurrency, and the notes are on page 87, and it's a lot of vocabulary words because there are new phrases that we have never used before, and so you're going to need to be familiar with it. And we started off a foldable that will help you out with it as well. But we're going to be talking about points of concurrency, and let's take a look at the word concurrent. Concurrent is when you have three or more lines, rays, or segments that intersect at the same point. So the key for concurrency is you have to have three or more lines, rays, or segments, and they have to intersect at the same point. Then you call those lines concurrent lines, rays, or segments. The point where they intersect is called the point of concurrency. And we're going to be looking at points of concurrency of special segments and lines and rays of triangles. So let's take a look at this picture. Hold on. So let's take a look at one of the special segments. It's called the median of a triangle. And the median of a triangle is a segment from the vertex to the midpoint of the opposite side. So if we take a look over here, here's an example of a median of a triangle. It starts from a vertex of the triangle and it intersects the midpoint of the opposite side. So that's a median. And actually triangles have three medians because you can draw a vertex from a line segment from the vertex to the midpoint of each opposite side. But in this case we only have one picture. Then we have something that's called an altitude of a triangle. And that is the perpendicular segment from a vertex to the opposite side, or to the line that contains the opposite side. So the key in this case is the perpendicular segment, and it has to come from a vertex to the opposite side. So if we look over here, here's an altitude. It comes from a vertex of a triangle, and it intersects the opposite side at a right angle. Now, not all the times will the altitudes be inside the triangle because not all the time will in order to intersect it at a perpendicular angle, perpendicular will it be inside the triangle. Then of course we know what an angle bisector is. It goes from the vertex and it intersects the opposite side, but in such a way that it cuts the angle into two congruent pieces. And of course we know what a perpendicular bisector is. In this case it does not start from a vertex of an angle, but it intersects the midpoint of an opposite side of a triangle at a right angle. So we're going to look at the points of concurrency for each of these, and each of these points of concurrency for all the medians or all the altitudes or all the angle bisectors and all the perpendicular bisectors have its own special name. So here we have a triangle, and here are the medians of the triangle. And as you can see, they start from the vertex and go to the midpoint of the opposite side for each of these medians. But they all do seem to intersect. And the point that they intersect is called the centroid. The centroid. And here's the centroid. And even as I change the dimensions of this triangle, you see that the centroid is always inside the triangle no matter what type of triangle we have. So that the points of intersection of the medians of a triangle is called the centroid. So again, the point of intersection of a median is the point of concurrency or intersection of all the medians of the triangle is called the centroid. Now let's take a look at the altitudes of a triangle. And as you can see, the altitudes start from a vertex and intersect the triangle at a perpendicular angle. The other side at a perpendicular angle. And as you can see, we only have one altitude that's in the triangle, and then we have several altitudes that are actually on sides of the triangle. What kind of triangle do you think this is? If you said right triangle, you're absolutely correct. But as I change the dimensions, if it's an acute triangle, then all the altitudes go through the interior of a triangle. And if I change it to an obtuse triangle, then one of the altitudes is inside the triangle and all the other altitudes are outside the triangle. But let's take a look at the case of an acute triangle. And as you can see, all the altitudes do intersect inside the triangle. And that point of intersection is called the orthocenter. We're going to name it an O. And as I change the type of triangle, you see that the orthocenter can be actually on a vertex when it's a right triangle, and it's actually going to be outside the triangle if it's an obtuse triangle. So the point of concurrency for the altitudes of a triangle is called the orthocenter. I know, weird words, but it's a lot of vocabulary, but that's why we made it foldable, to help you out, and that's why it's important that you take notes. Now let's go back to the angle bisectors. As you can see, here are the 3 angle bisectors of a triangle. They do start at a vertex and they intersect the opposite side, but they intersect the angle in such a way that it produces 2 congruent angles, as we can see. And as you can see here, that no matter what type of triangle you have, all the angle bisectors are inside the triangle by definition. So that means the points of concurrency is also going to be inside the triangle. And we call the point of concurrency for the angle bisectors the incenter. And I help remember it because it's inside the triangle. So it's, that's why it's the angle bisector. Point of concurrency is the incenter. And those notes are on page 83. The point of concurrency of the 3 angle bisectors of a triangle is called the incenter of the triangle. And we already have those notes. And last but not least is the perpendicular bisectors of a triangle. They do not have to start at the vertex of a triangle, but they do have to intersect the midpoint of opposite side of a side of a triangle. As you can see here, none of these perpendicular bisectors intersect or go through a vertex. But if I change the triangle so that it is a right triangle, I can see that the perpendicular bisectors don't always intersect inside the triangle. Sometimes they intersect outside the triangle, and that point of intersection is called the circumcenter. The circumcenter. And as you can see, for right triangles, the circumcenter is on the hypotenuse, the midpoint of the hypotenuse. For acute triangles, the circumcenter is inside the triangle, and for obtuse triangles, the circumcenter is outside the triangle. So we call that the circumcenter because, and we'll talk about why we name it the circumcenter and what that means in a little bit, but it's the point of concurrency for all 3 perpendicular bisectors. Now let's take a look at property of a centroid. As we can see here we have a median, and here we have the centroid from earlier cases. And the distance from the length of the median, AM, in this case is 5.36. But that length is made up of the distance from A to CE, which is 3.58, and then adding up the distance from CE to M. And as I change this triangle, those values are changing. But what I want you to take a look at is the ratio. If I were to take the length of A to CE and divide it by the length of the entire median, it's 0.67. So in other words, the distance from the midpoint, from the vertex to the centroid is 2/3 the length of the entire median. And the distance from the median, the centroid to the midpoint is actually 1/3. And this ratio is maintained no matter what type of triangle you have. So we have a property of centroids that is the medians of a triangle intersect at a point, which is the circumcenter, that is 2/3 of the distance from each vertex. So in this case, BP is 2/3 of the distance of the entire median, which is in this case, BF. And CP is 2/3 of the way of the distance of the entire median that intersects from, that goes from angle C. So that is CD. And that holds for every median. And AP is 2/3 of the entire distance, or the entire length of the midsegment AE. Let's look at the properties of an incenter, which is the point of concurrency for the angle bisect. If I have a circle with the incenter as its center, and that circle is contained entirely into the triangle, then that circle is called an inscribed circle, and the center of that inscribed circle is the incenter. So the notes on page 83 talk about the points of concurrency of an angle bisector. And it says that it is equidistant because it's on the circle from the sides of the triangle. Then that means that we have such the case that PD is going to be the same length as PE, which is going to be the same length as PF, which means these are the same length because they all are on circles on a triangle.